At lunch, some of you were asking sort of where are things going. So maybe I'll give you a little sketch of that. So now I'm going to do tensor product, pullback, and compatibilities. Among all the derived functors that are interesting in algebraic geometry, so the projection formula and cohomology and base change, this kind of thing. Tomorrow, so I guess that's Wednesday, Sasha is going to tell you about Serre duality. Both of us are going to do some examples of with spectral sequences. So this introduction to spectral sequences just now, if you've seen them before, maybe you were happy. If you've never seen them before, maybe you're dying to see some examples. And so we'll try to work those in. We wanted to. Just some examples. We were going to talk about induced maps on cohomology, but we've decided to. We're aware that we're going very fast, so we'll try to put some meat on the bones, not only in the exercises but also at the board, and then we'll talk about Fourier-Mukai transforms and functors between derived categories induced by objects on the product, is what that means. On Thursday, I'll talk about semi-orthogonal decompositions. And we'll have occasion to use the Grothendieck spectral sequence a lot in at least one of those examples. So hopefully many examples there. And then on Friday, Sasha will talk about triangulated and DG categories. So if you've been unhappy with the foundations that we've been doing with the homotopy category of complexes and all this kind of thing, DG categories are another approach to the foundations. We thought it was good for you to see both. And then next week, we'll have sort of three strands. So Sasha will talk about exceptional collections on P2, just P2 or other? And mutations. So this, I'll start this on Thursday, but then there's more than you can say in an hour, so Sasha will explore that for several days. And also the Bondal-Orlov reconstruction theorem. Orlov reconstruction theorem, which says that if the canonical bundle of your variety is positive or negative, then any derived equivalence to another variety is an isomorphic. The other variety is isomorphic, and the equivalence is one of the obvious ones. So the derived category is a very strong invariant for things of positive or negative curvature. I will talk about matrix factorizations. Both examples and foundations. And you're actually, in one of the exercises, the one with the quadric cone and the kernel of M is the image, that 2x2 matrix. You're already starting to meet matrix factorizations. You'll see a bit more of them on Thursday, but then next week we'll do them in earnest. And we'll need this DG foundations to do that properly. And then Ed Siegel, who's not here yet, but he will be, he will talk about variation of geometric invariant theory quotients and flips and flops. So when you have a birational map between two between two varieties, you sometimes get an equivalence. So he'll talk a lot about that. And then these two will converge into Orlov's theorem, which I'm not going to try to write right now, but that was mentioned in the abstract for the course. It talks about a semi-orthogonal decomposition of the derived category of a Fano variety, where the interesting piece is given by matrix factorizations. So that's where we're hoping to go. In particular, I'm sorry, I wanted to do more spectral sequence examples now, but I thought it was better to do the thing that lets you do the exercises we've already printed up. So we'll do that. Oh, and a correction from last time. I was a little cavalier in my definition of an adapted class, especially well, to be down to earth. So if we have f from x to y, we want to say that locally frees are an adapted class for f upper star. And I said that that should mean what? So that it should be, they should be closed under direct sums. Well, sure, the sum of two free modules is free, so the sum of two locally free sheaves is free. 3, that every sheaf is a quotient of 1, locally free. So we discussed that, at least for coherent sheaves on projective schemes, and you're going to think about it more generally. But then I also said that there should be that Li f upper star of a locally free should be 0 for all I bigger than 0. And that doesn't actually make sense. If you don't have enough projectives, then this thing doesn't have any meaning if there are not enough projectives around to define what it should be. So you shouldn't take this definition. You should take the other one, which is equivalent if you did have enough projectives. 2 should be that if I have a complex, so if E is an acyclic complex of locally frees, so that's saying, again, no cohomology, then f upper star E is still acyclic. So if you had LIF star, you could say that this implies this using a spectral sequence argument, right? That would take, right? It would take the derived, well, using a spectral sequence argument. But if you don't have that, if you don't have projective resolutions around, then this needs to be your definition. And you could prove this by working in affine patches where you do have enough projectives, I think. Probably be the best way to prove that. Okay, one more comment. Cohomology means two different things for us. So be careful not to be confused between the ith cohomology of a complex. So if I have a complex of objects in some abelian category, then I can talk about its cohomology and the sheaf cohomology and HI of X with coefficients in a sheaf, which is Ri gamma of. Right, so we're going to call them both cohomology, and there will be opportunities to get confused. So if you find yourself confused, just ask. Right. So earlier we had the derived functor of sheaf Hom. Right, so earlier we could do R sheaf Hom of F to something by an injective by. You could resolve the second term by injectives, or you could do R sheaf Hom like this. You could resolve the first term by locally freeze, by vector bundles. And we also had this business about R Hom of a complex to another complex, and the issue was you could replace this one with a complex of locally freeze or that one with a complex of injectives and then just go to town. So now we want to talk about the tensor product for if I want to do this tensor that one, derived tensor. It's the same story, but we need to use locally freeze on both sides. Well, on either side. So you need to define this, you either need to replace this one by a complex of locally freeze and then tensor them, or that one. And at the end of my first lecture, I mentioned this lemma that you needed to make it work was that if I take an acyclic complex and tensor it with a complex of locally freeze, it remains acyclic. And Sasha discussed that using a spectral sequence. And this story is the same story. And you can say, so a tensor product, so earlier we had to worry about whether a push forward of a injective sheaf was injective, and it wasn't, but we had the push forward of of a flask sheaf is flask. With tensor product of locally freeze is locally free. So we can say things like E dot derived tensor with F derived tensor with G is naturally E dot tensor F dot tensor G. Before long, we're going to stop writing these L's and R's everywhere. But for today, let's keep them. So you just replace everything with a complex of locally freeze, and it's true on the nose that this tensor product is the same as that tensor product. So next, we want the pullback. Yes? If I tensor together two locally free sheaves, then it remains locally free. And so what does this tensor product mean? Well, you could replace one or the other, or you could replace both. And then you do the plain old tensor product. And this is saying that, I guess what I'm saying is tensoring with a locally free complex takes this adapted class into that adapted class. Okay, so pull back if I have f from x to y. You have, let me just remind you something about the pullback. So you have this f inverse, which goes from OX modules to from OY modules to F inverse OY modules. And this is actually an exact functor. And this is the one with stalks everywhere that the first time you meet it is not very enlightening definition. And F upper star, well, you have part of the definition of a map of schemes is this F sharp from F inverse OY modules, from F inverse OY to OX. It tells you how to pull back functions on Y to get functions on X. This is part of the data of F. And so F upper star going from OY modules to OX modules takes F to F inverse F tensor over F inverse OY with OX. Right, so this functor was exact, and this one is right exact. And moreover, it takes quasi-coherent OY modules to quasi-coherent OX modules. And so F upper star is right exact, and the right exactness creeps in at this point. And as I wrote here, locally frees are an adapted class for pullback. So you have an adapted class which is locally frees. And therefore, you get LF upper star, which goes from bounded above complexes of quasi-coherent sheaves on X to bounded above on Y. And F star preserves this adapted class. F upper star of a locally free is locally free. So left derived G upper star after left derived F upper star is left derived G after F upper star. Just like push forward took flasks to flasks, and so this worked. Pullback takes vector bundles to vector bundles, and so that works. So you have an exercise. Maybe I won't write it, but to blow up the origin in the plane and derived, pull back the structure sheaf of the origin and see what happens. So I highly recommend this exercise. If you have to choose between that and the one with the check thing for flasks, don't do the check one. Right. So those are all our derived functors. And then we have a million compatibilities. So let's write them down and then discuss which ones we want to talk about. So we have compatibilities. So you get something like pullback of E dot tensor F dot is pullback of E dot tensor pullback of F dot, this kind of thing. And how does it work? You replace E and F with complexes of locally freeze, and then for locally freeze, you know that this statement is true on the nose. So these need to be need to be both in D minus, don't they? You have things like there are going to be about 5 of these of increasing interest. So Schiefhalm from E dot to Schiefhalm F dot G dot is Schiefhalm from E dot tensor F dot G dot. So again, this is true on the nose if let's see, if F is a complex of locally freeze and G is a complex of injectives. And let's make E a complex. Well, let's make E and F complexes of locally freeze. Then this will be true on the nose. Sorry, I left out an R, didn't I? So if E and yeah, everything should be derived. Am I? You're going to have to correct me 10 times. Thank you. Yeah. So in the underived version, you would know this was true if E and F are locally free. And so in the derived version, it's just true. In particular, if we take no, sorry, let me write my next one first. You have something like R-HOM of E, F, left-derived tensor with G is R-HOM E, F, tensor G. So again, if E and G are complexes of locally freeze, then you know this is true, and therefore it's true in the derived category. And in particular, if we take F to be just trivial line bundle, the structure sheaf, then this says that E dual tensor G is isomorphic to R-HOM E G. Actually, Sasha, do you prefer the check versus the star for dual? Check, okay. Where I'll tell you what the dual is. Where E dual is by definition R Schiefhalm of E O. Sorry? Yeah, he needs to be bounded, doesn't it? Yeah. is a bounded complex. Yeah, so why is this true? Because to do this Hom, I need E to be bounded above, and to do this, and then E dual will be bounded below. But to do this tensor product, I also needed E dual to be bounded. You think so? Or maybe you need G to be bounded. So to do this, E needs to be bounded above, and then that's okay. And now E dual is bounded below, and then the tensor product gives you trouble, right? You'll see why we very quickly decided we just want to do the bounded complex of coherent sheaves. By the way, if you want to read these things, in addition to the books that we mentioned, there's also Hartshorne's old book, Residues and Duality, which is typed in this old style and a little bit hard to read, and Brian Conrad's 300-page exegesis of residues and duality, where he goes through and corrects all the signs. And he's very good-natured about it. So Hartshorne's older book and Conrad's gloss. Right. So let's keep writing these, and then we'll go back and discuss for some of them what sort of boundedness hypothesis do we really need. So we have this adjunction. So if I have f from x to y, and let's say I have, well, I want to say that R Hom from f upper star of E to f of LF upper star E is R Hom from E to RF lower star F. That's the global version. There's also a local version. So let's think, how should this go? So what I've written can't yet be right, so leave a little space. E. Maybe it would help to say that this is happening on x, and this is happening on y. So this must be happening on y, and this must be happening on x. And so what I need to put here is an R F lower star. So how does this go? I need to replace E with a complex of locally frees and F with a complex of injectives. And then this thing is a complex of still of injectives, and so I can push it down. So if E is a complex of locally frees and F is a complex of injectives, or if it's a single locally free and a single injective, then you know this is true. And therefore, it's true for a complex of them, and therefore it's true in the derived category. And how do I get from here to here? To get from here to here, this is just global sections of this, right? Where can I put that? So to get from here to there, you can take global sections, right? Because global sections of F lower star of a sheaf is the same as global sections of G. And so R gamma of RF lower star of a complex is R gamma. And in particular, if you take H0 of both sides, you get that homomorphisms from this one to that one. Well, we haven't explained this yet, have we? That H0 of our Hom is really Hom in the derived category. We might need to say a word about this. Right, so F upper star and F lower star are adjoint to one another in the derived category because they were in the classical situation. You can imagine a few more variations on the things on this board, and you can ask yourself if they're okay. And the answer will be if you put the right boundedness on them so that they make sense, then they're okay. We have the projection formula. Which says that the push forward of E tensor the pullback of F is push forward of E tensor F. So to do this, I need to replace F with a complex of locally frees and E with a complex of injectives. And then, well, you know that it's true if F is a complex of locally frees. That's the kind of thing that's in Hartshorne. And so it works in the derived category. This is a very useful formula that we'll use all the time, especially on Thursday. I want to just take 1 second and tell you that you've seen this formula before in calculus. I want you to compare this to the integral. If let's see, the integral of a function of two variables times another function is the integral of E of xy. So if we were in a more topological mood, we would be happy to see push forward as a lot like an integral. And then, so what is it, right? I'm thinking of little f as being like the sheaf f. And pulling it back means taking this function of two variables and of one variable and regarding it as a function of two variables. Tensor product. Okay. This is more motivation than something serious. But when we go to talk about the Fourier-Mukai transform, you'll wonder why Fourier's name is there. So this will be relevant again. And why we call them integral functors and kernels and all this kind of thing. And then the most interesting one is cohomology and base change. So hopefully at this point you're really starting to like the derived category, because if you read this statement in Hartshorne, there was something about one of them has to be locally free, and if it wasn't, there would be some spectral sequence that he wouldn't want to mention. But in the derived category, it's just true, and then extracting the spectral sequence that would allow you to really compute is a matter of turning a crank that's the same for all of them, for all these compatibilities. These few boards here are where the derived category starts to shine. Right, so if I have x mapping to z via f and y mapping to z via g, and I'm going to put here W is going to be the fiber square, the fiber product. So I'll call this F tilde and G tilde. So this is a fiber square. And I want one of them to be flat. And can someone just tell me, in the exercises that you have there, do I talk about F upper star, G lower star, or G upper star, F lower star? G upper star, F lower star? So I want to, let's see. In that case, I want G to be flat. So G upper star is exact. So everything is acyclic for G upper star. So I don't have to worry about taking locally free resolutions. This is isomorphic to R F tilde lower star of G upper star. So if G is flat, then G tilde is also flat, that you can go like this and this, or like this and this, and it's the same. So this is something you know. Well, if G is flat, then you know this for the underived push forward, pull back. And so in the derived category, it's still true. Replace E with a complex of injectives. And there's an exercise, even if you don't have a fiber square, even if G is not flat, there's a natural map in one way or the other. And so you get to figure out which way that map goes. So maybe let's do some examples. So this is a simple example, but it'll be very important for us. Example is when Z is just a point. Right? And so every map has to be flat. So we want to start to get a sense of how to use this cohomology and base change. Right, so I have X to a point. I have Y. This is F. This is G. This is X cross Y. And I think probably this map, I'm going to call these maps P and Q rather than F tilde and G tilde because they're projections. Right? So given a complex E, where should E live? In D plus of Q co X. The statement is that P lower star, Q upper star of E R is G upper star R F lower star of E. But what I want to say is that if we're just mapping to a point, push forward to a point is the same as global sections. So this thing is just global sections of E, just sheaf cohomology of E. And then, well, the derived category of a point the derived category of spec K. This is the derived category of just K vector spaces. And this is just the category of graded vector spaces. So by an exercise that you did yesterday, because every exact sequence over a field splits, you can replace everything with its cohomology. And so now if I have a graded vector space and I pull it back, that's just taking OY and tensoring it over K with this graded vector space. So right. So if I take a complex of vector spaces, regard that as a so if I take, how about let's do it this way. So let's do a real example. Let's take X to be an elliptic curve. And E just to be OX in degree 0. Right? So R gamma, so the cohomology of OX is going to be K, so in degree 0, and K in degree 1. Right, so R gamma of OX is quasi-isomorphic to the complex that's just K to K like that. And now that's a thing here, if I pull it back to Y, that's just, the pullback of K is just OY. Which I think deserves to be called OY tensor over K with this. Right. In general, you can't just compute the derived functors and know, compute the individual pieces of the derived functor and know what the whole thing was. But when you're talking about a point, talking about vector spaces, you can. Other questions about that example? So I promised to explain to you why the derived push forward is cohomology along the fibers. And what did I mean by that? And now that we have cohomology and base change around, I think I can explain that a little bit better. So let's do another example. Let's do a slightly complicated example. I was going to put this in the exercises, but it didn't work out. So example. So let's still let E be an elliptic curve. And let's fix some point P naught in E, a point. Let's work over an algebraically closed field so we have a point. And then maybe you know every degree 0 line bundle on E is OE of P minus P naught for a unique P in E. And if you don't know that, take it on faith. Or we can talk afterward about how you get it with Riemann-Roch. And so the moduli space of line bundles on E of degree 0 is E itself. There's a natural bijection between line bundles on E and points of E. And you can make a universal bundle. So you have a universal bundle. On E cross E, which is, I'm going to call it L. It's going to be OE cross E. I'm going to think of this E, the horizontal E, as parametrizing line bundles on the vertical E. And we know that every line bundle can be thought of OE of P minus P naught. So here I need E times the singleton P naught, and here I need the diagonal. So it's going to be that of E cross P naught minus the diagonal. So these are both divisors in the product. And the point is that L, sorry, I have that backwards. I want the diagonal. Minus E cross P naught. And if I restrict this to a slice this way, if I'm over some P there, I'll restrict it to P cross E, which is, of course, just isomorphic to E. This is OE of P minus P naught. Right, so this L, if I've set it upright and not made any typos, is the point P in this downstairs E parametrizes this line bundle in the upstairs P. In the sense that if I restrict the universal line bundle to that orange slice, then I get the line bundle that I want. You might be happier if the moduli space and the space that the sheaves live on was different, but this example is really much simpler than any example I can describe that's like that. And now we need a couple of facts. First of all, if M, well, let's put it this way. The cohomology of OE of P minus P naught is either 0 and 0 if P is different from P naught, or K and K if P is P naught. So this is the cohomology of the trivial line bundle, and this is the cohomology of a non-trivial line bundle. Right, so what does all this have to do with cohomology and base change? And the fact that the derived push forward gives you cohomology along the fibers. So if I include P and E, and I'm going to map E cross E onto E as in that picture. So I'm going to call this P, pi. This is just a taste of something that hopefully we'll get to do more of later. Then what is the fiber product? The fiber product is just P cross E. It is this orange slice that I've drawn over there. And so let me call this I. Now, you're going to object that I is not flat, and maybe I'll call this J, and I'll call this var pi or something. So we want to say that that I upper star, that Li upper star of R pi lower star of L is R var pi lower star of Lj upper star L. Right, so this is the thing that we already computed. Right, so this is restricting L to that fiber. Right. It's here. And this is taking cohomology of it. That's here. Right, so this is either k goes to 0 via k if p is p naught, or just 0 if p is not p naught. Whereas this thing is more mysterious. Right? I need to take this thing and push it down and then restrict it. I started at quarter after, right? Yeah. Okay. And maybe it would be better, this right-hand side, I'll write it more cleanly. This was 0 if p is not p0, and this is k plus k shifted 1 to the right, which unfortunately is shift by -1. If p equals P naught. So here's a fact that we want to understand. R pi star of L is OP shifted by minus 1. Right, it seems like, so, but not OP plus OP shifted by minus 1, as you might guess. But Li upper star of OP is OP plus OP of 1. So this one we can understand. Okay, so in 2 minutes, I want to say a few things. Right? I want to explain this to you. This will remind you of some causal stuff that you've been doing in your exercises. Well, or maybe it's better to call this K plus K shifted by 1. So if you believe this conclusion, and you believe that this base change formula holds, which is fancier than the base change formula we had before, where I would have had to be flat, then you can agree that this fact and this fact are consistent with that one, whereas this fact and that fact are not. Let's understand this fact here. So we can resolve OE surjects onto OP. So I have my elliptic curve, and I have my point on it. And the point is a divisor on the curve, so the ideal sheaf of the point is the line bundle OE of minus P. So I have this map of line bundles here, which vanishes exactly at P and nowhere else. Oh, I lost a P naught. Sorry. These should all have zeros. Sorry. And so this is a locally free resolution of OP naught. And so L I upper star OP naught is going to be just K going to K. And this map is going to be 0 if P is P naught, and not 0 if P is not P naught. Because this map vanished exactly at P naught. P, right, so yeah, P naught was there. And P was wandering around. So we were restricting to the fiber at P. Sorry, I thought this example would not involve too much new stuff all at once. Maybe it does, and then we view it as a preview of things to come. Right, so what are the new ingredients here? First of all, a bunch of geometry. Second of all, this is, if this was mystifying to you, then this last board is the thing you should spend a little time trying to understand why the derived restriction of that skyscraper sheaf to another point is 0, but to the point itself has these two pieces. And then once we have Fourier-Mukai in hand, we'll talk about cohomology and base change in non-flat settings like this. All right. Sorry if that example was a bit much. So now we'll have exercises and then cake, and then what are we going to do in the problem session? Yeah, we might start discussing some solutions from the first day. So if you have ones that you particularly want to see, or solutions that you were particularly happy with, have those ready. Okay, thanks.